Thank you. All right, hello, you are Python. I've got a lot of content, so I'm probably going to talk pretty fast. Apologies for that. As I was introduced, my name is Peter Sobat. I'm a staff machine learning engineer at Spotify, and I work on a team called our Audio Intelligence Lab. Now, that doesn't really mean too much, but what we actually do is we teach computers to listen to music. We use machine learning to build systems that can listen to music automatically and tell us interesting information about that music. So some of our work is stuff that you might have seen on the internet or in open source. We publish things like this API here, which lets you get the audio analysis of any song on Spotify. So if you've ever listened to a piece of music and you wondered what key is that in or how fast that is or things like that, this API can tell you that for any track on the Spotify platform. But we don't just create APIs. We also open source things, like this thing we open sourced a couple weeks ago called Basic Pitch. Basic Pitch is a machine learning model that'll take any piece of music and transcribe it into the notes that were used to play it. So it kind of takes audio and turns it into digital sheet music, known as MIDI. And it's a fully open source machine learning model built in Python, available on GitHub there. Or if you want to check out basicpitch.spotify.com, it's available there in your browser as well. But what I'm here to talk about today is neither of these things, rather a different project that we've built called Pedalboard. Pedalboard is an audio processing library in Python. Now, Pedalboard lets you load audio, manipulate audio, edit audio, do all sorts of cool stuff with audio directly in Python in a very Pythonic way. And that's what I'm going to be focusing on today. So we're going to talk about 5 different top-level topics today. We'll talk first about what audio is, because this is EuroPython, not Euro Audio or something like that. We'll talk about how digital audio works and kind of give you a brief overview of how audio works in a computer. We'll talk about reading and editing audio in Python. We'll go on to talk about problems with audio in Python, and then finish off with audio effects with Pedalboard, which is really what it's good at, and we'll have some really cool examples in there as well. So let's start off with the absolute basics. Again, this is EuroPython. I don't expect any of you to have any knowledge of what audio is. Hopefully you know what Python is. But let's answer this first question of what is audio? What do I mean when I say audio? Well, if you ask the dictionary, it'll tell you audio is sound, especially when recorded, transmitted, or reproduced. But that's still kind of vague. What is sound? How does sound work at a really basic level? Well, sound is really just any vibration, any sort of vibration through the air that isn't too slow or too fast for our ears to pick up. Our ears are sensitive to a range of different vibration speeds, between about 10 vibrations per second all the way through to 20,000 vibrations per second, which sounds like a lot, but it's not that much. In this range, there's a whole bunch of different sounds that you've definitely heard before. In fact, everything you've heard is within this range. Towards the lower end of the range, you'll have sounds like bass guitars and rumbles and car engines and things like that, and those have fewer vibrations per second. In the middle of the range, you'll have sounds like the human voice and kind of higher pitched sounds, maybe musical instruments, a lot of stuff like that. And towards the top of the range, you have sounds like birds chirping and other kind of high-pitched sounds. So higher pitches mean higher vibrations per second, or technically, higher frequencies. These frequencies here are notated in a unit called hertz, often notated as Hz. And they're called hertz because higher frequencies hurts your ears. No, it's actually named after this guy, this German physicist, Heinrich Rudolf Hertz. But nonetheless, that's how sound kind of works at a basic level. So if that's how sound works in the real world, how does digital audio work? How do we get that into a computer, measure it, and play with it in our code? Well, just like everything else in a computer, we need to measure it in the real world to get it into a computer and start working with it. So let's do some of that measurement here. Let's measure this by putting a graph on the screen. And of course, we're going to need to put some axes on this graph. So we'll put time on the bottom, and then something called amplitude on the y-axis here on the left-hand side. Now, amplitude, I'm not going to get too much into what this means, but you can think of this as the position of the sound wave, or how if the sound wave is pushing towards you or pulling away from you, that's the amplitude. And we'll see that on the screen in a second here. So I'm going to play a sound, and I really hope this works. And as you hear the sound, you'll see some points show up on the screen. And that'll be me clicking a button on my laptop and recording the value of the speaker or the microphone here at each point. So let's try this. It worked. OK. So we've got a bunch of points on the screen here. There's not too many of them. They're not very detailed, you might say. But we've recorded the position of the microphone that was used to record this audio at various points in time. I was pushing the button roughly once every 0.4 seconds or so. And if we take the inverse of that, or the reciprocal of that, we get a value in hertz, again, that unit for frequency. And that value of 2.5 hertz here is what we call our sample rate. This is how often we sample the microphone and actually figure out where the microphone is at that point in time. Now, there's other things we can look at here. You notice that this graph is a little bit odd. It's got points at the top and the bottom, and that's because silence is not at the bottom of the graph. It's actually in the middle. And the top and bottom of the graph here are, very confusingly, both maximum loudness. We have maximum loudness in the positive direction at the top and in the negative direction at the bottom. And again, this is because sound is a wave. Sound is vibration, and it goes back and forth. So if it goes back and forth a very small amount, it's going to stay towards the middle of the graph. And if it goes back and forth a lot, it's going to hit the extremes. So maximum loudness, again, is the top and the bottom of the graph, very strangely. And then we can measure each point here. So we've got this point on the left, which might have 60% amplitude. So we could represent that as 0.6 in code. And we've got this point here, which might be 90% amplitude, but in the opposite direction. So we'll look at that as negative 0.90. So with this, we kind of have enough points to try to reconstruct what that sound was and reconstruct the entire waveform. But unfortunately, we really don't have enough detail here. I didn't push the button often enough for me to get enough information to reproduce what we just heard and to play it back, essentially. So now, instead of 2.5 hertz, let's re-record this again at a much higher sample rate. And you're going to see a lot more data on the screen here. So let's get rid of that and try this again. OK, so there's more points there now. There's a lot more points. In fact, you can't even see the individual points. We sampled at 44,100 points per second, or 44,000 hertz. And that's just a huge amount of data there. So we can't do much with what we're seeing right now. We're going to have to zoom in to actually see what's on the inside here. So let's do that. Let's zoom all the way in from the second scale down to the millisecond scale here. And as we get closer and closer, you can actually see the individual sound waves that were used, or that came out of that saxophone and went into your ears. And this is what your ears were vibrating like, back and forth in this pattern. Now here, if we measure the distance between these two peaks, not these points, but these two peaks here, we can actually see there's a duration in there in milliseconds. That's 5.7 milliseconds between peaks. And if we do a little bit of math on that again, do one cycle divided by that, we can find out even the frequency of the note that the saxophone was playing. So just from measuring that waveform over and over, we're able to find out the note. And I think that's actually an F, so that we can find out what musical note was being played there just by doing some math. But let's keep going even deeper. We're still only looking at the milliseconds level. Let's go from milliseconds down to microseconds, where we'll be able to see the actual samples. So now that we're super zoomed in, the actual samples look like little points along this graph. And we can measure, again, every single point at the microseconds level. And this gives us our representation of the audio. And here's the real secret that I want to tell to you all today. This is digital audio. This is all it is. Digital audio is really just streams of numbers. Nothing too complicated, although you can do complicated things with it. This is how you represent digital audio. So if this is how digital audio works, let's take a look at how we might store this in different ways. Let's zoom out a little bit again here. So what we're looking at here is called uncompressed floating point data. It's 32-bit or 64-bit floats. And this is pretty heavy. It's about 21 megabytes per minute of audio. That's a lot of data. If we had to store all that for every single song that you listen to, that would be, well, really expensive. It would take a long time to download, and so on. So people store audio in different ways. Sometimes we can store audio as uncompressed fixed point data, as 16-bit or 24-bit or 32-bit signed integers. And on the lower end of that, we get 10 megabytes per minute instead of 21 megabytes per minute. But that's still a lot. So back in the 90s, people invented some very, very clever compression codecs. These compressed floating point codecs, like MP3 and OGG and so on, compress all the way down to 1 megabyte per minute of audio, which is much, much easier to deal with. However, as you can see there, we're no longer actually looking at the numbers. We're not looking at the floating point values. We're just looking at encoded bytes. So to do anything with this compressed data, we're going to have to use a library or some other system to decode it, and then use the numeric information we get after decoding here. So that brings me smoothly to my next topic here, reading and editing audio in Python. So if that's how audio works in a computer, and that's how we might store it on disk, how do we get that into our Python code? Well, here's where I shill just a little bit for the library that I've been working on for quite a while, called Pedalboard. And we're going to start here by actually diving into the code. We're going to start by importing Pedalboard, by doing from pedalboard.io, import audio file. Now, in Python, if you want to open up a regular file, you use the open function. But here, we're going to use the audio file constructor, or the audio file, let's call it a function. And it's going to do the exact same thing. So we can do with audio file, my favorite song.mp3 as f, and that'll open a context manager for us, open this file up, and allow us to play with what's inside this file. It'll automatically decompress the audio for us and just give us data that we can deal with. So let's look at some properties here. We can do f.sampleRate to give us the sampling rate that we talked about earlier. We can do f.numChannels to tell us the number of channels that are in this audio file. Oftentimes, audio files have 2 channels, one for the left ear and one for the right ear. And then we can actually just read the data out of it. We can do f.read here, and we can ask for 3 samples, just the first 3 samples of the file. Now, Pedalboard is going to give us the first 3 samples in each channel, so we'll get back an array of a shape, or with a certain shape here. The shape here is 2, 3 for 2 channels, left and right, and then 3 frames of audio here. Now, if you're not familiar with multidimensional arrays, they're not too complicated. You can kind of think of them as arrays of arrays, but in this case, each subarray has the fixed shape. So we can just use that shape parameter to see what shape the overall array has. But OK, if that's how we can open a file, what can we do with the audio once we pull it out of that file? Let's give that a try. Oops. Just to illustrate here, the left channel of the audio is the first array here, and then the right channel is the second array. So we can actually separate these out very easily like that. But going back to the start here, let's take a look at opening up another audio file. And instead of just reading in 3 frames, let's read in all of them. Let's do audio equals f.read f.frames. Now, f.frames here is just a property that tells us how many frames we have in the entire file. And here we get back an array with a certain shape. Again, 2 channels, so that's left and right as the first dimension, and then 1.3 million samples as our second dimension. So channels first, and then samples afterwards. So from there, we can then look on to actually decompose this audio a bit. We can do audio at 0 to give us the left channel, audio at 1 to give us the right channel, and you can see there are arrays with totally different contents here. So they don't have to be correlated with each other. And then using Python's array slicing syntax, we can start to chop up this audio and edit it, trim it as you would. So we can do audio and then pass in an empty slice for the first dimension, and then a slice up to the first 100 samples for the second dimension. And that'll give us a stereo chunk of audio or a stereo array that contains only the first 100 samples. But 100 samples doesn't really mean too much for us. It just tells us that's 100 points. What does that mean in terms of seconds or in terms of duration? Well, to get that, we can do some math using f.sampleRate here. So again, the sampling rate we talked about before, we can ask for the first 10 seconds by using just regular Python array syntax and doing f.sampleRate times 10. We can also ask for the last 10 seconds with the exact same array slicing syntax, negative f.sampleRate times 10 there. OK, so now we know how to read audio and kind of play around with it as an array and slice it up. What can we do with it, though? We've really just opened up an audio file. How can we make it maybe sound different or look different, something like that? So let's go all the way back up to the top. Let's read in our MP3 file again. And this time, let's just whittle it down to 1 channel. Just get the mono audio, or 1 channel from the left channel here. Now let's try to change how this sounds. Instead of just playing with a regular audio file, let's add some delay to this. Let's add some echo. This is the same effect that you might have if you're in a big space and you might hear a slapback echo of your voice coming back from the back of a room, which is actually what I'm hearing right now. But let's add that to this audio file with some code. And let's see how few lines of code we can write in Python to make this happen. So let's set some parameters first. Let's set delay seconds equal to 0.2, or 1/5 of a second. So let's make our audio delayed by 0.2 seconds. And then let's convert that into samples so that we can deal with this as like array offsets rather than floating point numbers here. And then we also should set another parameter here, which is how loud our echo or how loud our delay is going to be. So let's set that to volume equals 0.75, which is 75% of the original volume. And now we're going to do some math. Don't get scared. It's actually fairly simple, but we're going to do a little bit of math here. So we'll iterate through the original array. We'll do for I in range len mono, so just iterate through all the samples in the original array. And then if we have enough room to add echo afterwards, so if I plus delay samples is less than the end of our array, then let's add some delay. Let's do mono at I plus delay samples plus equals mono at I times volume. So that's a little confusing to think about, but let me give you a quick visual example to see what this means. So let's play with a smaller array, maybe something where our delay is only 1 sample. And let's say our signal looks like this. We have 6 samples, 0.0, 0.1, and so on. What we're essentially doing here is taking a copy of this array, multiplying it by volume, and then shifting it forward by the number of samples we want to delay. So we'll shift it forward like that, add the results together, And then the result is essentially the original signal plus also a delayed copy that's a little bit quieter. But I'm still just showing you a bunch of numbers on the screen and a bunch of math. What if we can hear this? And the great thing about working with audio code is that you often can hear what you're doing and what it sounds like. So let's listen to a signal before and after it's gone through these 7 lines of code. No delay, sounds normal, sounds like a little piano. And now after going through this code. Kind of cool, right? With only this code that you see on the screen here, we're able to take the actual audio signal you just heard and alter it in a way that our ears can make sense of, right? We've done something kind of neat there. But let's not stop there. Let's do some even more extreme effects by writing some Python code. So let's get rid of that, and now let's load up a new file. Let's load up something here called coolguitar.wave, which is a cool little guitar sample. Again, let's read in the audio file with f.read. We'll read all the frames in the file and just take the first channel. Then let's make this guitar sound a little more extreme. Let's add some distortion to it. So we'll set some parameters here, like the amount of gain that we want to add here. What's the unit on gain? To be honest, I actually don't know here. This is just a multiplier we're going to multiply our signal by. And the higher this number, the more extreme it's going to sound. Now we'll also set an amount of volume that we want to multiply this by. So if we have a gain level of 200, we're going to knock this down by 90% and take only 10% of the original signal's volume, because if we're going to distort this, it's going to sound pretty loud. And then just like before, we're going to iterate sample by sample over the entire array here and change the value of each sample. So here, instead of doing any sort of delay or array offsets, we're just going to modify every single sample in place and say mono at I is equal to math.tanh of mono at I times gain times volume. Now you might be asking, what is math.tanh? And that's for a different talk. I'm not going to get into the math of this, but you'll be able to hear this in just a second. So let's listen to coolguitar.wave before our processing. Sounds like a guitar. Now this is going to be a tiny bit louder, as you can kind of see on the screen there, but don't cover your ears. I don't think it should be too loud. So that sounded a lot more metal, a lot more high energy, if you might say. And all we had to do to make that sound is the code that you see on the screen there. In fact, this is even less code than what we had to do to implement some delay. So with very small amounts of code in Python, you can actually alter sounds and edit sounds like this very easily. Okay, so I've talked about a couple cool things you can do here. Let's talk about problems you might run into working with audio in Python. Python is great, working with audio code is great, but sometimes there are some rough edges that make it really difficult to work with Python code, or with audio code in Python. So let's start with, well, a similar example to what we had before. So let's load up my favorite song.mp3, and let's say we want to do something different with this file. We want to load it up and make it louder, and then save it back to disk again. So we'll do with audio file here. We'll do audio equals f.read, f.frames, and then once we've read in the audio, we'll make the entire thing louder. We'll make it louder by multiplying it by 2, which takes each sample value and multiplies by 2, and then we'll save the result back out to disk again. We can use Pedalboard for this by doing with audio file out.mp3 and passing the W flag as the second parameter, and then passing in the sample rate because we need to know the sample rate in order to save. And then we just do o.write, and like any other file, we've written that to disk. But there's a problem here. This code will probably run just fine on your laptop, and it'll run just fine on all the test MP3s that you have or the small audio files that you have. But what happens if the input is not something you control? What if that audio file at the top is not actually a small song or a small MP3 file you have, but something that a user gives to you, or something that comes in from a web service, or it's, you're running this on a large catalog of audio? What if that is 2 hours long? Well, if that MP3 file is 2 hours long, you might not really be able to tell that until your code crashes, because once you read all the frames in, that ends up being 2.3 gigabytes of audio. And this is something kind of deceptive about audio in general, is that because of audio compression and because of how effective audio compression is, you can actually have very small files that uncompress to massive, massive amounts of audio in memory. So there are very simple techniques we can use to get around this. And one way to do this is by chunking the audio and processing it in chunks instead. So let's try that here. Let's set a chunk size of 500,000. Let's open up our input audio file, and let's open up our output audio file as well. So we're kind of nesting these context managers, really just so they'll fit on the screen. I know you can put them all on one line. And then as long as we have audio to read in, so while f.tel is less than f.frames, so as long as there's more audio coming in, let's read in a single chunk of audio, process just that chunk, make it louder, and then save just that chunk to our output file. And now with this, we no longer use 2 gigabytes of memory for a 2-hour-long file. We only ever use up to 4 megabytes of memory here. And this input file could be 2 hours long or 20 hours long, or it could be a stream that never ends. And our code is still going to work because we're processing in chunks instead. So what I really want you to walk away with here is not chunking or that exact line of code that you saw there, but that you should think of audio as a stream. Audio is really a stream. It's streaming in time, and time keeps going. Audio could keep going for as long as you want. So if you write your code such that audio is a stream, your code will be more resistant to bugs and will probably not crash in production, or at least not as often. OK, so let's look at one other common problem with audio in Python here. And let's go back to the example we had with distortion, that really cool guitar example. So here's the code that we had before. I'm not going to type it all out again. But we read in our entire audio file, and then we do math.tanh at the bottom here. Now, I said I wasn't going to get into what tanh is, and I'm not. It's a mathematical function. But we're looping over every single sample here in Python. And this is fairly fast, or at least it's fast enough. If I run this on my laptop, it takes about 8 seconds per minute of audio to run this code. So that's a good way you can measure audio code, is you can take how long it took to run and divide that by the amount of audio that you process through that code. And here we find out that this code runs in what's called about 7.5 times real time. So 7.5 times faster than it would be to just play back the audio itself. However, that still seems a little bit slow. If I have to run this on a minute of audio, I have to wait 8 seconds, and I'm very impatient. So is there a way to do this any faster? Well, luckily, Python has a lot of libraries and a very rich ecosystem. So I found that you can use NumPy, the numerical computation library, to do this exact same operation. And instead of doing math.tanh there, which only takes in a single sample at a time, we could do numpy.tanh, which takes in an entire array at a time and then processes that through the same function. The results are exactly the same. In fact, byte for byte, they're identical. The sample values are perfect. But this code at the bottom runs a little bit faster. And when I say a little bit faster, I mean it takes only about 23 milliseconds per minute of audio. That's a great gasp. I'm glad that happened. Yeah, 23 milliseconds per minute of audio. So that's a little bit faster than the old code was. In fact, if we do a bit of math here and divide these two, it's about 338 times faster to use a library here instead of manually iterating over the samples. In our case, we used NumPy, and NumPy made this 338 times faster, but you could use Pedalboard, or you could use really any other library that optimizes this away. And the last thing I want to talk about here is really that for audio, pure Python is slow. I hope I'm not offending anybody with this statement, but pure Python, iterating through samples and doing direct math, can be very, very slow compared to native optimized C code, essentially. So if you can, use third-party libraries instead. OK, and that brings me to my final section here, which is talking about audio effects in Pedalboard. So we've talked about how to do some of these effects ourselves and how to make this sound really good in pure Python. But what if we use this cool library that I've been talking about to do some of these effects for us? So I'm just going to jump directly into the code here. Just like we had before, we're going to read in an audio file. And even though I just told you not to read in the whole file at once, I'm going to do it here because otherwise it wouldn't fit on the slide. And I'm going to use Pedalboard to import some audio effects. So I'm going to import an effect here called reverb. So I'll do from Pedalboard import reverb. And then we'll create an instance of this reverb effect. We can do that with reverb equals capital R reverb and set the room size to a certain amount. So room size equals 0.75. Whatever that number is, it's just between 0 and 1. I don't think there's actually a unit on that, but it's good enough. Then we can take our input signal here and pass it through our reverb plugin. So affected equals reverb, pass in the audio and pass in the sample rate. And all of a sudden, we've applied an effect to the audio, and it now sounds different. But you don't have to trust me on that. You can actually listen to it. So let's listen to Cool Guitar Wave before and after once again. And now with the reverb applied. So musically, that's the same. But you can tell that something has changed about that. It sounds like it was played back in a large room or kind of a bit more boomy, a bit bigger. And that's a common effect that musicians will apply to their audio. So let's keep going there. Let's get rid of the reverb example there, and let's chain multiple effects together. So instead of just applying one effect, let's make an entire pedal board that contains multiple effects. So here we'll do board equals pedal board, which is really just a list or a container for multiple effects. And let's add a distortion effect first, followed by a delay effect, followed by some reverb on the end. Now, this is actually very similar to what we did before in pure Python, but now we're just chaining these plugins into an object that's much easier to deal with. Then just like before, we'll take our audio signal and we'll pass it into the board. So we'll do affected equals board of audio and f.sample rate. And again, we have a before and after comparison here. It's not the same sample. This one's a little bit more tuned for the effects that we have here. But here's the before. And then when we put this through some distortion, delay, and reverb, it sounds very different. In fact, it sounds kind of musically interesting as well. It's not just affecting the tone of the sound, but it's changing the musical content too. Okay, I've talked about some guitar examples and stuff like that. What about other use cases? What if you're not using Pedalboard with music or you're not affecting your music here? What if you have a podcast that you want to process? So let's read in a podcast voice sample here. We can make a pedalboard that works on podcasts just like the guitar pedalboards we've already done here. So let's add a noise gate to get rid of some background noise. Let's add a compressor to make quieter parts of the sound louder. Let's add a low shelf filter, which is really a kind of equalizer or EQ. And then we'll add some gain on the end to make the entire thing a little bit louder. Now with these 4 effects in series, we'll take a voice that's kind of not really radio ready and turn that into a voice that sounds a much more professional voice, basically. So we'll pass the audio in here. And then again, I'll give you a before and after. And apologies, it's going to be my voice, which you've heard already throughout this talk. But yeah, here it is.
Welcome back to the podcast, where I talk about podcasts.
So that's me recording my really cool podcast. And then once it's gone through this pedalboard here.
Welcome back to the podcast, where I talk about podcasts.
Much more full, much more boomy, arguably, but really sounds more radio ready compared to what I've got there. And then my last example here, my last 2 minutes, are how you can use Pedalboard to load other plugins as well. I've showed you a bunch of effects, reverbs, distortions, things like that. But if anybody in this room produces digital music or uses a computer to produce music, you've probably heard of plugins or audio plugins, VSTs, audio units, and things like that. And Pedalboard lets you take all of those and put those directly in your code and call those from Python. So again, let's read in a guitar sample here and read in the entire audio file into an array. Then let's load a third-party plugin. So I'm going to do plugin equals load plugin, and I'll pass a path to a VST here. So chowcentaur.vst3. Whoops, that's going too fast. Oh, damn it. Okay. We'll load a third-party plugin here. And that third-party plugin will have code in it that we didn't write. And in fact, it's not even written in Python. So it's code that you might have downloaded on the internet or purchased from somewhere else, because VSTs are things that you can buy anywhere. So we'll load that plugin, and then we'll also do plugin.showEditor. Show editor here will actually open up the plugin's UI, and directly in Python, you can play with the buttons and change the sliders and do all the sorts of stuff you might do in your digital audio workstation. Then just like before, we can run audio through it. We'll do print plugin.gain to change certain parameters. We'll set plugin gain to 1.0 for maximum rock. And then audio goes through, and here's the before and after one last time. And afterwards, now we couldn't have written that in Python. We're just going to use someone else's code for it, and it sounds pretty good. So with that, I'm out of time. If you're interested in using Pedalboard, you can find it on GitHub at github.com/Spotify/Pedalboard, or just PyPI. It's available on PyPI there, pip install Pedalboard. Thanks so much for listening. Find me in the hallway for any questions you might have, or for cool stickers of the nice Pedalboard logo we've got there. Thanks, EuroPython.
Nice timing, Peter. On the dot. So everyone, as Peter mentioned, we do not have time for Q&A, but I'm sure there's a lot of questions in your mind. So Peter will have his Q&A at the hallway. Line up if you have any questions for him. Can we have another round of applause for Peter, and thank you for your talk.